sketch f of x equals to negative x plus 1 to the power of 4, x minus 2 to the power of 3, and x minus 1. We're now up to possibly the most advanced part of the polynomials course, but also this happens to be the most exciting part, at least to me, because we'll be able to sketch any high degree polynomial by hand just by looking at the form when it's fully factorized. So to begin, the way that I break down the strategy to be able to do this is I look at 3 steps of analyzing the equation and figuring out how it looks. Step 1 is we'll identify if the leading power of the polynomial is odd or even. So remember, the leading power is the highest power. And if your question is given to you in fully factorized form, you can do this by just looking at all of the x's, looking at all the powers that are applied to the x's, and then combining them together how they would with index laws, right? So from the first bracket, I would have an x to the power of 4 as my highest power. From my next bracket here, I would have x to the power of 3 as my highest power, and from this bracket, I have just an x to the power of 1 as the highest power. So when you multiply all of those together and combine them, you get an x to the power of 8. Okay, so this is a strategy that you can use with your brackets to figure out the leading power without doing the full expansion, because that would be a lot of steps to do the full expansion, and we don't really need that. We just need the leading power. So in this case, the leading power is even. And an even leading power tells us that the graph will start and end by pointing in the same direction. A good example to compare to, which we know is an even-powered polynomial, is a parabola. So we know from experience that parabolas look like this, right? So on the left and the right, they point in the same direction. And this can be extended to any high-power polynomial with an even leading power degree. We can have any sort of shape going on around here, but it will always start and end by facing the same direction. And parabolas can obviously also be reflected, right? So a parabola can be reflected, but then it's still facing in the same direction. It's just facing, they start and end facing in the same direction. It's just facing down, right? And the same thing, any higher power one can also do a whole bunch of stuff here, but it will start and end by facing down if the power is even. Now for an odd power, it's just this, the opposite of that, right? So if I have an odd power, which is my leading power, then my graph will point in opposite directions. So the best thing to compare it to is a cubic. We know a cubic starts and ends in opposite directions. And so if I have a higher power, I can have any sort of thing happening, but it will start and end by pointing in opposite directions. And exactly the same, if I wanted to think about a reflection for the cubic, it might, like a reflected cubic could look like this. So it starts and ends just in the other side. And I can do the same thing if I have a really high order one. It might start and end in opposite directions like that, but it's still, it can have anything happening in the middle, right? But the very ends at positive and negative infinity are going in the different directions to one another. So that's what the first thing tells you. When you look at whether it's an odd or even, you'll know whether it does something like this and then starts and ends in the same way, or whether it does something like this, where it starts and ends in opposite ways. Now, step 2. I will identify if the leading term is positive or negative. So that determines the reflection of the overall direction of the graph. So to identify that, I will have to go through all of my x's and look at what's multiplying each of them, including any coefficients at the front and taking into considerations any powers. So it's very similar to this first step, but I'll also include any coefficients. So the coefficient -1, that's from the front. Then I have, from this bracket, this is just an x to the power of 4. From this bracket, it's just x to the power of 2. Oh, sorry, 3. That's a 3 in there. And then from this bracket, it's just an x. So you can see, after all of these, when I multiply them together, I get negative x to the power of 8. So my leading power in this case is negative. Okay? So what does that tell me? And this is where it was coming to those reflections that I was talking about. Essentially, there are only 4 scenarios that you can have. You can have even, you can have odd, leading powers, and then you can have whether it's positive or you can have if it's negative. and this is all the different options that you can have. So a positive even one starts and ends at the top. So they point in the same direction for an even. It can do something in the middle, and it will start and end pointing upwards. Just like imagine comparing it to a positive parabola. I always go back to thinking about how parabolas and cubics work because it's what I'm used to, and I can imagine those ones pretty quickly for positive and negative. So a negative even will start and end in the same direction, but it's pointing downwards now because it's negative. So imagine a reflected parabola would look like that. Okay, so that's for a positive and a negative even graph. So if I'm looking at, I'll come back to this in a moment, so I'll just do the odd side now. So a positive odd one, imagine comparing it to just your regular x cubed. That can start and on the bottom here, then it can do something in the middle, and then it will shoot upwards in the opposite direction. So you can see they start and end in opposite directions, which is what we said for odd ones in step 1. And it's sort of got that overall positive kind of slope that we spoke about with cubics. So it starts at the bottom and then goes towards the top. Now for negatives, it's the reflection of that. So it will start at the top, it will do something in the middle, and then it will go down. So it still has opposite directions, like what we said for an odd one, but it's now, so it's got those opposite directions, but now overall, it's sloping kind of downwards. It's starting from positive infinity on the left and going down towards negative infinity on the right. So these are the only 4 scenarios that you need to know, which is exactly what steps 1 and 2 are helping you figure out. So if you understand how these work, if you can find whether it's odd or even, and then you find out if it's positive or negative, you now have an idea of the overall shape or like the direction that it's going in. And then the last thing will be to just figure out what's actually happening with these little curvy bits in the middle. Now, the way I like to remember, or the way you can write it down for positive or negative, is we always look at the kind of top right-hand quadrant, or quadrant 1. This is looking at quadrant 1, which is where x goes towards infinity. So if I imagine each of these on some axes, okay, when x goes towards infinity for the positive one, then you can see y goes towards positive infinity. So that's what this one says here. When x goes towards infinity, if the graph is positive, it's going towards positive infinity in the y direction. Then for the negative one, it's opposite. In that last quadrant, when x is going towards, x is still going towards infinity, but now y is going down. You can see that y is heading towards negative infinity in those examples. So that's what step 2 is telling you, but essentially in step 2, you should be picturing something similar to these graphs that I've drawn here, and just selecting which of these options we're drawing. So for this question that we're doing, we have identified that it's an even leading power. So we're looking at the even column, and then we've identified that it's a negative graph, so we're looking at this one. Our graph will look something like this. It will have something in the middle, but it will start and end in the same direction, and it will be pointing down due to being negative. All right, so hopefully that's making sense so far, because now we're up to the really fun part, which is identifying the specific behavior which happens at each of these little curvy bits. So this is based on the factorized form. So we have to make sure that what we're looking at is the factorized form for this step. What we look at is each individual bracket, which should correspond to an x-axis intercept from our null factor law. And then based on each bracket and based on the power of each bracket is what we'll decide happens at those x-axis intercepts. So first of all, if it has no power on that bracket, so for example here, that's where it will just cut the x-axis. It will just go through the x-axis at that point. So corresponding to this bracket, I'll have cut the x-axis. Then, if the bracket is got an even power on it, then there is a turning point here. So the graph will just touch the x-axis. It will go through the x-axis, but it will turn around there. That's like when we had that repeated root in cubics. So this is an example of where we'll have that. So we have an even power on this bracket. So this is where it will have a turning point. Turning point. So it will just touch the x-axis and then it will turn around and go back. Okay, and the last example that we can have is if it's an odd power on the bracket, and in this case there's a point of inflection here. So it still cuts the x-axis, but there's a bit of a curve happening where it cuts. So that's an example of this last bracket. We have a cubic. So in this case, this will just have a point of inflection at that point. Okay, so now we have enough, based on these three kind of criteria for each bracket, we have enough to classify each x-axis intercept, and then we'll have enough information to draw an exact sketch, or well, not exact, but we'll have the idea of what the shape looks like. Okay, so let's actually give this a go. I've gone and analyzed, while we were looking through the notes, I've gone and analyzed this graph here. So I've figured out that it will have this overall shape based on the leading power being 8 and based on the leading power being negative. And now we know it's got this overall shape, so now all I have to do is look at the things that I've said happen at each of those intercepts and then decide how to draw that from there. So my x-axis intercepts, I'm going to let I'm going to let y equal to 0 for my x-axis intercepts. So I have x plus 1 to the power of 4, x minus 2 to the power of 3, and x minus 1. So x plus 1 corresponds to x is negative 1. And that's where I have a turning point. X minus 2 corresponds to x equals 2, and that's where I have a point of inflection. Finally, x minus 1 corresponds to x equals to 1, and that's where I'm just going to cut the axis with sort of mostly like a straight looking line, nothing special happening there. Okay, let's go and label those points. Starting out, I'll have negative 1 here, I'll have positive 1 here, and then I will have 2 over here. Now my shape looks like this. So I'll start by heading from negative infinity up, right? So imagine it goes towards negative infinity there. I'm heading up. And then as I get to my x-axis intercept, the very first x-axis intercept, I have to go and check what's happening there. So that's this one. I have a turning point at this x-axis intercept. So I'll go up to it, and then I'll just touch it and turn around. Okay, so I've gone through that point, but I've turned around. I've got a turning point there. The next point I get to, I can see is 1. So at 1, I'm just going to cut the x-axis, right? So I'll kind of sweep around, have some sort of point where I sweep around, then I'm going to come and cut the x-axis at that point. And then finally, I've got to go back through this very last point where I can see I've also got a point of inflection. So I'm going to turn around, return here, and when I do return, I'm going to have a point of inflection. So it might look like this, bit of a point of inflection, then I'll change the curvature, and then keep going down. And remember, I've got to end facing the same way as I started. So that makes sense because we've gone through, done the correct behavior at each of the x-axis intercepts, and now I can see I'm facing in the right direction, which makes sense for an even-powered polynomial. Okay, so I've got actually a really good shape. I won't be able to find the turning points that aren't on the axes unless I've studied calculus or unless I have a calculator with me. But this is enough to know the general shape. And finally, one more thing that I can label is the y-axis intercept, which is really easy to find. So I'm just going to let x equal to 0 so that I can find that really quickly. I have f of 0 equals 2, so negative 0 plus 1, which is 1, 0 minus 2, which is minus 2, and then 0 minus 1. So I have minus 1, 2 to the power of 3 is 8, but it's negative 8, so minus 1 times minus 8 times minus 1. So it's just equal to minus 8. So my y-axis intercept is at 0, minus 8. And that's the coordinate here, which I can label. Okay, awesome. So you've just drawn your first higher order polynomial with all these curvy bits, and we were able to do it in just 3 steps. The first step was to figure out whether it will have the ends facing in the same direction or in different directions. Then we had to figure out, is it starting and ending at the top, or is it starting and ending at the bottom, which we figured out based on the fact that it's a negative overall, all the x leading powers multiplied to give a negative coefficient. And then finally, we could figure out the shape just looking at each of the x-axis intercepts, which we could find from each of the brackets, and then looking at the powers on the brackets to figure out the behavior at each.